let's try and make it possible and safe and commercialize it. So this then shows the lithium-ion architecture in comparison with the Quantumscape architecture that we have, where we have what we call an anode-free design. So there's no anode in the as manufactured state. We have a separator that interfaces to a current collector and nothing present in the anode side. The cathode is relatively similar. Both the active materials and ion conductors or catholyte inside the cathode share a lot in common with lithium-ion batteries, but we've replaced the anode with nothing in the manufactured state. And then all the lithium that's in the cathode material as manufactured will, on the first charge, come and plate at this interface between the separator and the current collector and form this block of lithium metal at the anode side. And then this is the lithium that cycles back and forth as you charge and discharge the cell. So one of the keys here to enabling this architecture is the separator. So we replaced the porous polymer separator with a dense ceramic separator here that sits between the anode and cathode. And it's this separator that's a key, I think, to enabling lithium metal, as we'll talk about. So what does this change enable in terms of energy density? So this is a map then of mass-specific energy density, or watt-hours per kilogram, on the y-axis, and volumetric energy density on the x-axis, showing the range of commercialized chemistries from lithium iron phosphate, or LFP chemistries, which are low energy density but low cost, to what's more common in electric vehicles, at least the ones outside of China, using an NMC or as Tesla uses NCA cathodes. So these batteries are going to improve by, we're projecting several percent per year as you go to more nickel-rich cathode chemistries and include more silicon on the anode. But what we're hoping to enable is really a pretty impressive change relative to what's typical in batteries. Of single-digit percent per year improvements in energy density by switching to this lithium metal architecture. So that's the target. In terms of energy density, by removing the host material, we hope to improve on energy. By eliminating this lithium diffusion bottleneck that I talked about, we hope to enable fast charge. By eliminating this SEI formation and growth, we hope to improve in life. By eliminating a lot of the flammable materials in the cell, we hope to improve in safety. Then a further benefit in safety is, if the car gets in a crash or has some over temperature event, the polymer separator can melt. And then as it peels back, it'll expose more contact area between the anode and the cathode. And that contact area can result in internal short circuits, which delivers a lot of energy to heat the battery very quickly, that is part of what can lead to this chain reaction or thermal runaway. So this is why that most modern separators today will start to include a layer of some ceramic particles that are still porous. The purpose of those ceramic particles is to try and prevent this thermal runaway by putting something that won't melt in between the anode and cathode. Well, our separator is this entirely dense ceramic material, so I think we achieve that effect, hopefully to a greater extent. And then in terms of cost, as I've described, we eliminate the anode manufacturing step and materials, so hopefully we can lower costs as well. So this change, we hope to address these 5 metrics simultaneously. Now, as I said, we didn't invent the lithium metal anode. That concept has been around for decades, but it has been hard to commercialize, and this is why you don't see a lot of cars today driving around with lithium metal anodes. So people have tried various different separator chemistries between organics and inorganics. There are many families of materials that have been attempted to work with lithium metal: liquids, gels, solid polymers like PEO. Among inorganics, there are sulfides and oxides are the most popular classes. Also emerging over the last few years are halides, borohydrides. Unfortunately, all of the materials that have been tried have real challenges on at least one, if not more, of the key metrics for the separator. So when it comes to the separator, some of the key requirements, at least in the automotive space, are it needs to have a high bulk conductivity, competitive with liquid electrolytes. If you think about it, it's pretty impressive to have lithium hopping through a solid matrix as quickly as it'll transit through a liquid, but it is possible in some materials. Then the interface to the anode needs to be as conductive as possible. One of the things that's a little bit subtle and sometimes underappreciated is that there can be as much resistance at just the interface between the lithium metal anode and the separator as there is throughout the entire bulk of the separator. So to be able to have a high power battery and enable fast charge, you need to have a low interfacial resistance. ASR is an area specific resistance. The separator is going to be in contact with the anode and cathode over the life of the cell, and also in contact with both the 0 volts relative to lithium on the anode side and the high voltage of the cathode side. So maintaining stability over that very wide range of activity of lithium. It's about 80 orders of magnitude of lithium activity when you go from 0 to 4 volts. 80 orders of magnitude is, it's such a large number. It's literally astronomical number. There's something like 10 to the 80 atoms in the universe. So the 80 orders of magnitude of lithium activity, it's like saying you have, metallic lithium on the anode side and 10 to the minus 80 lithium activity on the cathode side would be 1 atom of lithium per atom in the universe. It's just a huge range of lithium activity. So for a material to be stable across that full range is extremely challenging. And then, of course, dendrite resistance is probably the biggest challenge here. So as described earlier, when lithium plates on the anode, it tends to form these dendritic structures that bridge across to the cathode and result in an internal short circuit. Dendrites tend to form exponentially more aggressively as you increase the current density during charge. So as you go to a fast charge requirement, it becomes very difficult. And I'm not aware of any really compelling demonstration that a cell can resist dendrites over many cycles and realistic automotive conditions. So that's a big challenge. Then finally, the separator has to be made thin, comparable to today's polymer separators, process it continuously, not in batch modes or high vacuum processing, to enable low cost over large areas. So it's really a difficult challenge. And if you're not able to meet that challenge, well, there are a couple of sort of fallback positions or compromises, either to revert to a hosted anode and use carbon or a carbon silicon anode again, or use excess lithium, at which point you're really diluting the advantage that a solid state battery can have relative to lithium ion in terms of energy density and cost. Or you might have to compromise the test conditions and sacrifice some of the real world operating conditions that automotive market expects, to go to either slow charge rates or thin cathodes, low cycle life, or limited temperature range, and, for example, run hot only. And so these are sort of the compromises one might have to make if one doesn't have a separator that can meet all of the requirements on the last slide. So that's sort of the landscape. Now I'll talk in more detail about Quantumscape status and really go into the data of where we're at right now in solving all of these monumental challenges. So on the left is a photo of our separator. It's roughly the size of a smartphone. It's shown here. It's quite flexible. That flexibility is not required in operation. It'll be just flat in a cell like what's shown in the middle, but it does speak a little bit to its robustness when it's thin. You know, for those of you who are familiar with handling thin silicon wafers, even a silicon wafer that can get quite flexible as it's thin. So it's pretty impressive what thin films can do. And this is an image of our single layer pouch cells, again, roughly the size of a phone. And then image of our multi-layer prototype cells over here on the right that we've been developing over the last year. So let's start off getting into some of the data. This is a cycling data from from batches of our single layer pouch cells in this form factor. And it is, I think, one of the most impressive demonstrations of dendrite resistance that our cell offers. So I'm showing the discharge energy on the y-axis and cycles on the x-axis here. The commercial target that Volkswagen has set for us and that we're setting for ourselves is 800 cycles to 80% fade. For context, typical EV warranty today would be somewhere in between 100 and 150,000 miles to 70%. So somewhere where my cursor is right here. We're trying to get to this 800 cycles to 80% target here. Why 800 cycles? If you have a long range electric car of say 300 miles, then if each cycle is 300-mile range, then 800 cycles give you 240,000 miles. That's pretty considerable to 80% fade. And so then this is showing batches of our cell performance here going out to over 1,000 cycles, cycling quite well under conditions that are listed in this table here. So we're also trying to be transparent about the test conditions for every test. And so we'll give you the test conditions here. This is at a 1C, 1C rate, so 1 hour charge, 1 hour discharge. That's pretty aggressive for a cycle life test like this that's typically done at C/3, meaning 3-hour charge. So this is 3 times higher current density on every charge. The cathode loading of north of 3 milliamp hours per square centimeter is getting thick enough to have real energy in the cell. The temperature of 30 degrees is near room temperature. We're using the anode-free lithium metal anode configuration that I've described, going full depth of discharge over the full commercially relevant areas. Pressure is something I'll talk more about in a minute, but these tests are done under relatively modest pressure on single layer cells. So I think this was a pretty exciting proof that the materials and the processes that we use to make these materials are really capable of withstanding real world conditions, or even more aggressive than real world conditions here. So then fast charge is, another really key requirement, we think. So how do our cells do in fast charge? So this is, in blue here, is data that we collected on cells in our lab showing fast charge capability. So the y-axis is the state of charge over time on the x-axis. So we did here a 4C charge rate, and you can see the cell charging up quite quickly. It beats this target we have set for ourselves of 80% in 15 minutes. What's shown in gray here is data that we didn't take in our lab, but we found that was published on a leading automotive cell hooked up to a supercharger that in 15 minutes gets to about 50%. And then the charge rate really has to taper off after then to avoid this problem that I spoke of earlier of lithium plating. So to get to 80% takes about 40 minutes in these type of cells. So this cell was again the same cell that I described on the last slide in terms of cathode loading, temperature, anode area, pressure, number of layers, and so forth. So It's the same cell that can do fast charge. Then we wanted to really test dendrite resistance of the separator itself. So we took the separator out of a cell and did a stress test where we just increased the current density and saw at what current density can the separator withstand. So we're passing small amounts of lithium and then increasing the current density, pass more lithium and increase the current density, and continue to increase the current density here. So many solid state efforts could do south of 1 milliamp per centimeter squared, or up to about 1 milliamp per centimeter squared. To get to the 4C charge rates that I described earlier, that's 12 to 16 milliamps per square centimeter, depending on cathode thickness. We went all the way to north of 100 milliamps per square centimeter across the separator without failure. And so then this is showing the corresponding voltage that develops across this lithium-lithium cell. This test was done at 45 degrees because that's really the condition probably most relevant to fast charge. I think most fast charges, the car will already be driving, and so the batteries will be somewhat warm, and then they'll also heat up due to their internal resistance as you charge. So 45 degrees is a pretty relevant fast charge condition. We were doing this in a lithium-lithium configuration because a cathode really can't deliver this kind of current density. 100 milliamps per centimeter squared is just far north of what a cathode can sustain for long periods of time. So again, this is the materials level test. It's not inside a cell, but you can think of it just as a stress test to show a factor of safety above a real world operating condition. So this is, I thought, a pretty compelling demonstration of dendrite resistance. I'm not familiar with any other results that get anywhere close to this, frankly. If I'm happy to be contradicted in the Q&A. Please speak up if you know of otherwise. So then we put the separators back into a cell and ran what I think is really the most stressful test that I've seen done on our cells. This is a track cycle that we got from our automotive customers. So to just describe this track cycle for a minute, this is showing one lap around the simulated track here. So just to be clear, our batteries weren't actually in cars driving around the track. We just took this drive cycle and did it on our single layer pouch cells. So this shows current density over time of one lap around the track, accelerations of 4 or 5 C here, and regenerative braking of 1 or 2 C, and then repeating this very aggressive accelerations on the straightaway, braking going into the turns, and repeat around one lap of the track. And then we repeat to get to about 9 or 10 laps around the track until the battery is fully depleted. And then we go into a 4C fast charge. And then we just repeat that cycle of laps around the track until the battery is fully depleted and 4C fast charge. Do that continuously. And so then this graph shows 2 of our cells and how they perform on that test, showing pretty gradual fade for over 1,200 laps around this track. This test is quite stringent. So if you put a leading energy cell that came from a leading automotive on the same test, it fades much more quickly, just because this is a very aggressive test. And again, all the test conditions listed here, this was done on the same generations of cells that I've been describing in the last few slides. So next, temperature performance. One of the knocks against a solid state battery is that they have to be hot to run. I think maybe that intuition might come from polymer cells that need to be heated to 60 or 80 degrees to have sufficient lithium ion conductivity. So we wanted to show that our materials are capable of running across the full automotive temperature range down to minus 30 degrees C. So this just shows a single C/3 discharge at decreasing temperatures from 0 degrees down to minus 30 degrees C. In between each of these discharges, we would do a C/3 charge at 30 degrees just to get the full charge capacity. So this is really just showing discharge capability of the material system. And for comparison, this is again the same leading automotive cell here at minus 25 degrees, showing that it gets less capacity than our cells do at minus 30. So in the right solid state system, they can run across the full automotive temperature range. So then we wanted to show cycling at low temperatures. So this would be representative of sort of real world winter driving conditions. Minus 10 degrees C, charging at C by 5 and discharging at C by 3 repeatedly. So this is showing performance of our cells, across winter, showing that they retain a lot of capacity. And then again, these were the same generation of cell, this single layer pouch cell, same cathode thickness, everything else. So I think solid state cells can work well at low temperature. This is some encouraging evidence. Next, let me come back to this pressure point here. So